So this is an example problem dealing with circular motion. In this problem we have a 1,500 kilogram car going around a curve, and the curve has a radius of 80 meters, and the car has a constant speed of 5 meters per second. And we want to find out what the net friction force on the car's tires. So what kind of force would allow the car to curve at that speed? So I have a picture below, and this is looking at it from the top. We have the car going straight. Well, it's curving, but this is its velocity at that instant, and that is 5 meters per second. And this is the path, of course, on the road, and that path has a radius of 80. I'll just write down R for the radius, and we have a mass for the car. I'll leave that off. And then we also have a force pulling it, and this is what's making it curve. So this is our force, and it's a frictional force, commonly used. We commonly use a small f, but in any case, it's just a force, the frictional force in this case. So to solve this, we're really going to use Newton's second law, but apply it to rotational motion or centripetal force, which is how people commonly refer to it. But it really is just Newton's second law. It is just, so we're getting the answer now, it is just the net force, or the sum of all the forces, is equal to mass times the acceleration. Now this is a vector equation, or we can break it up into its components, and that's what we're going to do with any rotational or circular motion problem. We break it up into one direction, which is the centripetal direction, the direction pointing back towards the center. So where I have, look back at the picture, I'm darkening in, the direction of this force here, that is the centripetal direction because it's pointing back towards the center of the circle. So we just want to sum up all the forces that are pulling back towards the center of the circle, and there's only one, that is the frictional force. So that's the left side of that equation, and then that's equal to the mass, and then times the centripetal acceleration. And anytime we have centripetal acceleration, or the acceleration towards the center of the circle, we can replace that with one of two things. The centripetal acceleration is equal to v squared over r, the speed squared over r, or it is equal to r times omega squared. That is the angular speed squared. This is probably the more common substitution, but in any case, either one of those can be useful. So now we'll go ahead and replace it with speed squared over r, because those are the variables that we were given. And now at this point, it really is just plug and chug. We have f on the left side, that is our unknown. We have 1,500 kilograms. We have the speed squared, so that is 5 meters per second squared, and that's on the top. And then we have the radius down below, 80 meters. And my calculator tells me that that is 469 newtons. And that is all there is to that problem.